So today we will start with Thomson scattering, and this scattering is by free electrons of the medium. So before coming to Thomson scattering, let's just have a look at what is scattering and what are the kinds of scattering and how Thomson scattering is different from other kinds of scatterings. So basically, scattering is defined as a process by which particles suspended in a medium of refractive index diffuse a portion of the incident radiation. You can see that there is a gamma photon is coming. It interacts with the charged particles here, and its path changes. And also some other particles can be emitted during the process, but that's different in different interactions and scattering that we will study later on. And in the process, no energy transformation results, only a change in the spatial distribution of the radiation. And the function of the ratio of the particle diameter to the wavelength of the incident radiation is given like this. And we have about five major scattering processes. The first one is the Rayleigh or the Raman scattering, and this is by bound electrons of the medium. And under in this, the it is occurs in the visible region, and the energy involved is of the order of electron volts. Another one is the photoelectric absorption, where the spectrum is in X-rays, and the energy is of the order of kilo electron volts. The Thomson scattering that we will be studying right now is also in the X-ray spectrum, and the energy is of the order of kilo electron volts. We have Compton scattering, where the gamma ray emission takes place, and the energy is about million electron volts. And in the pair production also, we have gamma rays, and the energy is also in MeVs. So broadly, we have to study these three kinds of scattering. The first one is a Thomson scattering, which is a classical concept. Classical treatment is involved in it, and it is the scattering of a photon by an electron. You can see in this diagram, a photon is coming and is scattered by the electron. The second is the Compton scattering, which is the quantum electrodynamical needs the quantum electrodynamical explanation, and it is also a photon and electron interaction phenomena. The third is the Rayleigh scattering, which is a coherent scattering, and it involves interaction between the photon and the atom. That means the bounded particles. And the Thomson and the Rayleigh scattering are the classical phenomena, like we just saw, and are elastic only in the direction of the photon changes and not in the energy. And if you are asked about how does a photon scatter, then the answer is the Thomson scattering. And to analyze Thomson scattering, we start with some assumptions. The first one is the wavelength of the light is as small as compared to the atom, and the energy of the light is light large compared to the binding energy of the atomic electrons. Third one is the energy of the light is smaller than the mass relativistic energy. And this kind of a radiation, which is by the free electrons, is described by the classical electromagnetic theory. And it is a low energy limit of the Compton scattering. The particle's kinetic energy or photon frequency do not change as a result of the scattering. And the limit is valid as long as the photon energy is much smaller than the mass energy of the particle. And if the wavelength of the light is much greater than the Compton wavelength of the particle. In this case, the electron will emit electromagnetic wave of the same frequency and in same phase that of the incident wave. And the electron will absorb energy from the electromagnetic wave and scatter it into different direction. That means only the spatial coordinate will change. And in particular, the wavelength of the scattered wave is the same as that of the incident wave. So basically, the wavelength is the same, the frequency is the same, only the direction is changed in the spatial terms. And it was first explained by Sir J.J. Thomson. And the main cause of the acceleration of the particle is due to the electric field component of the incident wave. And in the first approximation, the magnetic field of the incident electromagnetic wave can be neglected, and the particle will move in the direction of the oscillating electric field, resulting in the electromagnetic dipole radiation. The moving particle radiates mostly in the direction perpendicular to its acceleration, and the radiation will be polarized in the direction of motion. And depending on where the observer is located, the light is scattered from a small volume may appear to be more or less polarized. So the light that is obtained after the scattering is the polarized light. And in the due course, you will see how it is polarized. And the major applications of this Thomson scattering are in the cosmic microwave background. This polarized component mapping are called E modes and were first detected by Daisy in 2002. The solar quick corona is the result of the Thomson scattering of solar radiation from the coronal electrons. There was a NASA SOHO mission and the NASA Stereo mission that generated three-dimensional images of the electron density around the sun by measuring the corona. It is also applicable in tokamaks, the artificial nuclear fusion reactors that we are planning. And the corona of the ICF targets and other experimental fusion devices. The electron temperature and the density of the plasma is quite high. So we need the Thomson scattering to detect the high intensity laser beam. And the inverse Compton scattering can be viewed as also as the Thomson scattering in the rest frame of the relativistic particle. The X-ray crystallography is based on Thomson scattering. And now we come to the theoretical treatment of Thomson scattering. Start with how do we define a scattering? Scattering is when an electromagnetic wave or radiation passes through a substance or medium, it is absorbed by the electrons of the medium. This electron is set into vibration. And due to this vibration, the path of the incoming electromagnetic wave will get changed, and during the course some of the energy has been absorbed by the electron. So now the electromagnetic wave or the radiation will be having a lesser energy and the direction also will have been changed. So let us draw a picture. We have a target. There is an electromagnetic radiation coming. This is the incident wave. This is our scatterer. This is a normal. Now this is the main part. So basically, if we say that if radiation consists of a single particle, then this will be the path of that particle. But actually, the radiation consists of a number of photons. So it will be scattered in a conic shape, and such is called a solid angle. The change path is at a theta degree from this axis and a phi degree from the north. And the surface area of the conic created is called ds, and the solid angle, this angle is d omega. So these are the notations that we have to come across. So the first quantity which is important is the differential scattering cross section. We can define this quantity as the average energy per unit solid angle per unit time scattered in the direction making an angle theta, making angles theta and phi divided by the average energy per unit area per unit time in a direction normal to the incident wave. This is denoted as this. Divided by average incident energy per unit area per unit time. That means the average energy is scattered in a unit time and a unit solid angle. For the scattered radiation, we have the solid angle divided by the incident energy, average incident energy per unit area per unit time. So the only difference is per unit area, and here it is per unit solid angle. the energy scattered per unit time of this density of scattered energy per unit area per unit solid angle per unit time. From this we can say the solid angle is written as, so substituting the value we will get therefore the differential scattering cross section incident. Plus intensity. Here you can see that this quantity is dimensionless. This has dimensions of area. So this quantity has dimensions of area. Now the second quantity is total scattering cross section. So it is defined as the total energy per unit time is scattered in all directions divided by the intensity of the incoming plane wave. This we have written this formula on the previous page. I will integrate to obtain the total scattering. I will integrate this. So this is total scattering cross section. Now, for studying any kind of scattering, what we need to calculate is the differential scattering cross section and the total scattering cross section. These are the two basic parameters that we should know for analyzing any kind of scattering that takes place in any medium. So we will be dealing with two kinds of scattering. The first one is the scattering by free electrons. And this is called Thomson Scattering. And the other is by the bounded electrons, and that will be called Rayleigh scattering. So first we will be understanding the Thomson scattering, and we consider an electromagnetic wave moving in z direction, and its electric vector is in x direction. So this is how we represent the electric. And the force due to this electric vector will be, since the motion electric vector is in x direction, so the force can be written as and the right side taking in here. The solution of this equation will be what does this equation signify about the electron? The electron is oscillating with the frequency omega and will behave like a dipole. This oscillating charge will behave like a dipole, whose dipole moment can be given as dipole moment. Substituting x, where I have defined this quantity as P0, that is a constant amplitude. Now the oscillating dipole will radiate energy. So the average energy radiated per second per unit area, this is given by the Poynting vector, whose average value now the differential scattering cross section combined. This quantity is the classical electron radius. I have already written this value before also. Here I have directly substituted the value of this. Now let's, for an understanding, let's calculate this. Substituted the value of Q from the previous page. Let us see the diagram. The angle from this place to this is theta. From here to here is phi. And d omega is a solid angle in 3D. In 2D, this angle is alpha. The solid angle, when represented in 2 dimensions, is alpha. This is an incident radiation. This is our electron. This is the vector R. So we have two components of this vector R. This one vertical and horizontal. The vertical component will be sine theta. Similarly, this one will be Substituting OM from this is now ON upon R. This will be cos of alpha. Therefore, cos square alpha will be sin square theta into cos square phi. Sin square alpha will be 1 minus cos square alpha equal to 1 minus sin square theta cos square phi. Again reducing this. For the plane polarized wave, phi is equal to 0. So when phi is 0, I will open this and the sin square alpha will become cos square theta. Substituting the value of sin square alpha, substituting this. If the wave is unpolarized, or I can say randomly polarized. In that case, substituting the sin square alpha, theta is called scattering angle, and this term is called degree of you can write S or Z, whatever, both are. From here, what we can say is scattering is independent of, it is dependent on coordinate R and theta. So it is independent of incident beam. It is maximum, and this will be 1, when theta is equal to 0. Or the other value will be at 5. The minimum will be at depends on nature of charged particle. Why? Because of this R0. This is the classical radius for an electron. If the particle is different, then R0 will be different. The total scattering cross section is denoted as sigma t. This was the differential scattering cross section, and its integral will give me the total scattering cross section. Now substituting the value of d sigma by d omega, we will take R0 square outside, and the value of the solid angle differential will be, this is from the solid geometry, pi r will take outside. Here it will be d theta. Multiply this, this will be the value of total scattering cross section. R0 is 154. All the quantities are constant in R0, and these are also constants. Pi is constant. So the value of the total scattering cross section will be constant. Let's calculate it. Nine. This is R0 square, whole square. On calculation, the value comes out to be now the incident radiation is plane polarized. This will be 2 pi and R0 square outside. Yeah. We have already calculated the differential scattering cross section. We plot this expression, theta on the x-axis and the left hand side on the y-axis. So this kind of graph we get. Now there is another graph with the quantum mechanical picture. We are not going into the details of the quantum graph. This is the classical. This is the quantum picture. What I want to say is stresses initially both the classical and the quantum pictures are alive. In the limits, the theta tending to zero, both the classical and the quantum pictures are alive. And the scattered radiation is always in the forward direction. The scattering energy is concentrated in the forward direction. And the frequency of the scattered radiation is equal to the frequency of incident radiation. And at pi by 2, the scattering is symmetrical. So this completes our Thomson